Now let's talk about the factors that influence the solubility of chemicals in water. So we already know what the solubility is. Let's say we looked it up in EpiWin or we looked it up in the textbook. But now we might need to make some adjustments to that textbook value. We might need to adjust for temperature because everything depends on temperature. And as we discussed, we're going to have to think about how solubility might be affected by salinity. In other cases, if our molecule has some acid-base chemistry, we might have to think about how pH might change the solubility. And then there's other things in water, like dissolved organic matter, that could affect solubility. And as I promised, we're going to talk a little bit about co-solvents. All right, how does temperature affect solubility? So, like every other equilibrium constant in the world, we have an equation of this form. Natural log of Csat at T2 divided by Csat at T1 is equal to some enthalpy term divided by R, and then multiplied by the difference in the reciprocal temperatures. So as always, the big question is, what is this term? How big is it? So here it's written as HEW, that's the excess enthalpy of dissolution in water, and that would apply if the compound is a liquid, right? So we could write this equation. And we saw from that previous table that this excess enthalpy of dissolution is usually small for small molecules. Sometimes it's positive, sometimes it's negative, but it's frequently pretty small. And it's only when you get to really giant organic chemicals that the HEW term becomes large and positive. So if the enthalpy term is positive here, it means that the solubility increases as the temperature increases. Because a positive enthalpy term means you need to input energy in order to dissolve the compound, and at higher temperature you have more of that energy available, so the overall solubility of the compound will go up. But we also have to think about what happens to the solubility of compounds that happen to be solids or gases, right? So I've drawn this handy-dandy little roadmap to try to help you understand. Here we have the energy state of the pure solid. Here's the energy state of the pure liquid. Here's the energy state of water, and here's the energy state of the compound when it's a gas. Now, if we were going to draw this to scale, the gas energy state would be like way up here because, remember I keep telling you that to get an organic chemical into the gas phase is like launching the space shuttle. It takes a lot of energy. So really this should be way up here. It should take a lot of energy to get up to the gas phase. But anyway, if we're talking about a pure liquid compound dissolving in water, then the amount of energy required is right here in green. Okay, that's this HEW term. But if we're talking about dissolving a solid into water, we have to cover not only this distance, but we have to cover this distance too. We have to include the delta H of fusion. That's the energy required to melt the solid. Okay? And so the sum of these two things would be this whole distance, and that is what we might call delta H for dissolving this compound in water, a solid compound in water. Okay, so that would be this term right here. Now, if the compound is a gas, then here is the energy required to dissolve the gas in water, right? And that would be a combination of the energy required to dissolve the pure liquid minus the energy that you get back when you condense the gas. So you're starting here, you're condensing the gas, and then you're dissolving it in water. And so the net of those two is right here, which is what we're calling delta H, water to air. So for solids, the delta H term that you're going to use in that equation is HEW plus delta H of fusion. And for gases, the delta H term you're going to use in that equation is HEW minus delta H of vaporization. And notice that delta H of vaporization is usually large and positive, so if you're subtracting it off here, you're going to end up with a negative term. This is going to end up being negative right here. And so if delta H is negative, remember we just said that if delta H is positive, that means that the solubility goes up when the temperature goes up. Well, if delta H is negative, that means the solubility goes up as the temperature goes down. That's why gases are more soluble in cold water than they are in hot water. And that's why, for example, oxygen is so highly soluble at very low temperatures like in the Arctic. So we could draw this out. So here's our natural log of solubility over here on the y-axis, natural log of Csat. And here's 1 over T, inverse temperature here. And I've drawn 1 over the boiling point and 1 over the melting point here on the graph. So when the compound is a gas, you actually have, remember, because this is 1 over temperature, this direction is cold. Cold. And this direction is hot. Right? Yay, I can write with my cursor. It's hot. So at high temperatures, when you're a gas, gases actually become more soluble as the temperature goes down. For liquids, if we assume that this HE term is positive, that means that their solubility goes up as temperature goes up. So as temperature goes down, solubility goes down. And for solids, definitely solubility is going to go down as temperature goes down. So we have this sort of the three-phase weird sort of plot here where we have 3 different slopes, depending on whether we're talking about a gas. That's not what I meant to do. We have 3 regions here, depending on whether we're talking about a gas, a liquid, or a solid. And they each have different slopes. It's possible that the liquid could be going up or down, okay? But definitely the solubility of the solid is going down as temperature goes down, and the solubility of the gas is going up as temperature goes down.